Hello, everybody.
It's midnight.
Dr. Stone, you can disregard my email, by the way. I found it, obviously.
Yeah, I saw that. I was just going to email you when I got on, and I saw that you had, you're already on, so. All right, got a lot of people today. What do we have? 19? All right, so I trust that everybody has the activity for today. Right, everybody? Looks like it. Okay, all right. Let me know if you don't. Should have been on your Blackboard. Good. Okay. Oh, Alexander did not. Well, I will see if this works. If it doesn't work, you'll have to go to Blackboard and get it.
Don't worry about it. I got it. I got it. We're good.
You're faster than me.
Sorry.
Okay. All right. So today's activity is going to be based on a little bit of review when we talked about thermodynamics, but we are going to consider thermodynamics and kinetics at the same time. And so what you're going to notice is that when you think of chemical reactions, you don't just consider the kinetics, you don't just consider the thermodynamics, but you consider both aspects, right? You want to know if the reaction is going to be spontaneous at, say room temperature. And you also would want to know, like, is the reaction, reasonably fast? Can I do this in a lab period? Let's say if you're in organic chemistry. Well, so what you're going to start to notice is that just is thermodynamically favorable, it may not be kinetically favorable. An example of that is the formation of diamond. Okay, so we all know that diamond takes a really, really long time to form. Okay, so that would be considered not kinetically favorable, but at the same time, it's spontaneous. Okay, so the delta G is negative. So we take the two things separately, but we have to consider both of them. Okay, and so that's what this activity is all about. All right, so I was thinking what we would do is we'll work together on this, and but I'm gonna have you guys do calculations. Okay, so does everybody have a calculator ready?
Oh yeah.
All right, so we looks like we're all good. Okay, so we're gonna all have our calculators ready because I'm gonna call on you at random and you guys are going to have to be able to come up with numbers for me, okay? All right, so that is what you guys are gonna do with me. Okay, so let me share my screen. Okay, so here is my screen. This is the reaction of the day. All right, so we have the structure of methylcyclohexanone. And what you can see here is we have two different protons, and each of these different protons have different reactivity. So our job is to figure out which of these hydrogens are going to be removed. And we're going to look at the thermodynamics of the system, and then we're also going to look at the kinetics of the system, okay? So here we have a ketone. So we have our double bonded O. And the difference between these protons is one is not what's called sterically hindered. All right, so you can think of it as the base is easy to get to. And you have the other proton B that is sterically hindered because of that methyl group that's right there. So the base is not as easy to get there, okay? So the question is, what product do you expect to form? Do you expect to form product A, where we remove proton A, or do you expect product B, where we remove product B? Okay, so some things to think about is that in order for a base to remove proton A or B, it must break a CH bond. Okay, so that's what the base is doing, it's breaking that CH bond. And it says here that it's much easier for a base to abstract a proton that is less hindered. In other words, the proton with less steric crowding, or those bulky atoms around it, will be able to easier to accept the base, because the base can get in there a lot easier. Okay, so I'm going to stop sharing my screen and we're going to talk about this. Okay, so which proton, A or B, do you think is less hindered? Okay, so Jake says A. Yeah, all right. Oh, A's are coming in. Nobody says B. Everybody thinks A. Perfect. Okay. Okay, so that's good. So everybody understands now that that A is less hindered because B has that methyl group on it. Okay, so I'm going to share my screen again. All right.
Wait,
So,
Dr. Cohen,
yeah,
that's only less hindered strictly because there's less molecules around it?
exactly. So we'll say functional groups.
Yeah, all right.
Yeah. So that methyl group on that's right next to that proton is impeding the base from getting to it.
All right, sounds good. Thank you.
Yeah. Okay, so, all right, so another thing to think about is thermodynamics. Okay, so for molecules containing C double bonds, more to the alkene tends to be more stable. Okay, so let's go back to those structures. All right, so product A or product B, which one is more substituted for that carbon-carbon double bond? All right, which one would tend to be more stable? A or B? All right, so Jake is saying B. Charlene is saying B. All right, everybody's got B. Perfect. Okay, so now we have a conundrum, right? So we think that the proton A is less hindered and therefore easier for the base to get to it. But at the same time, that carbon-carbon bond of the product is more stable because it is more substituted. All right, so what should we do? Who would like to do a thermodynamic analysis of this reaction? I am sure everybody is screaming in their heads, I want to do a thermodynamic analysis of this thing.
I'll take a stab.
Awesome. All right, so this is where we get our calculators involved, okay? Okay, so now, so now we have a conundrum. Now we have to think about, okay, so what's the thermodynamics of the thing? So we're given a table of the thermodynamic parameters. And what I want you guys to do is I want you to calculate the entropy of product A and B, and I want you to calculate the enthalpy of product A and B.
That's using the
Okay.
summation of the products and reactants.
Exactly. So we're going to take the products minus reactants for the entropy for A and B, and products minus reactants for the enthalpy of A and B. So we should come up with 4 numbers. All right, so I'm gonna call on 4 people and you guys are gonna be responsible for your one number, okay? All right, so Jake, since you've already been talking to me, I want you to calculate the entropy of product A,
All right.
okay?
I got a second, right?
Excuse me?
I got a second, right? You don't need the answer right now.
No, I'm gonna call on other people.
All
And we're
right.
gonna take a couple minutes here, yeah. How about Lexi? I want you to calculate the entropy of product B. All right, and let's say Emily, I would like you to calculate the enthalpy of product A. Okay, Charlene, I would like you to calculate the enthalpy of product B. All right, and we're gonna give our classmates a couple minutes and then we're gonna talk about it. Oh, Charlene's asking me. Yes, I want the enthalpy of B. Thanks, Charlene. So you're just going to use that table that is table 1. All right, do you guys give me a thumbs up when you or have it completed so I know? All right, Jake is done.
You want me to go ahead or do you want me to wait?
Let's wait. Yeah, let's wait one more minute and then we'll go ahead.
All right.
All right, Jake. So tell me how you calculated the entropy of product A.
So the entropy is found, as I said earlier, through the summation of adding all the entropies of the products. You subtract the summation of all the entropy of all the reactants. And since it's 1-to-1, I only have the entropy of product A, which is 351.4 joules per mole Kelvin. So then I subtracted 313.8, which is the methylcyclohexane. And I got an entropy of 37.6 joule per mole Kelvin.
Okay, good, perfect. All right, so I think it was Lexi that had entropy of B. What did you get, Lexi?
I'm still working. I think I'm doing this like totally wrong. I'm sorry.
Okay, here, let me share a whiteboard and talk you through it.
Okay, because right now I have negative 0.882, which I don't think it's right.
No, it'll be positive. Here, I'll just share a whiteboard.
Okay, thank you.
So going from what Connor was talking about, so we're going to just do products minus reactant. So the entropy of B is equal to the product, which is 367.6. And we're going to subtract from it the reactant, which is 313.8. Do you see where I'm finding that on the table, Lexi?
Yes.
Okay, And then I have 53.8. And that's in joules per Kelvin mole. Okay, sound good?
Yeah, I see it now. Thank you.
Mm-hmm. All right, so who did we have doing product A? Oh, Emily. What did you get for the enthalpy of product A?
I was doing it wrong too. I was doing the same thing that Lexi was doing. And right now I was trying to like pay attention so I could fix it, but I don't think I still got a negative number.
For the enthalpy?
Yeah.
Okay, here. All right, so the enthalpy is the other part of the table, right? All right, so the enthalpy of A is equal to product. So we're talking about product A. So negative 260.3, and subtract from it the reactant. So negative 267.8. All right, and that is equal to 7.5 kilojoules per mole. All right, sound good?
Yeah, my problem was just that I was subtracting it by the wrong number, but I'm good now.
Okay, awesome. All right, and Charlene, what did you get for the enthalpy of B? 5. Okay, she got 5. Good. All right, so what she did was she took product B for the enthalpy, which is negative 262.8, and subtract reactant, which is negative 5 kilojoules per mole. Okay, so let's think about those numbers. Okay, we have a very favorable. Can you guys hear me?
Yes.
Okay, good. It just said my internet was unstable, so I was worried. Okay, so we have a very favorable entropy, and we have what we'll say an unfavorable enthalpy because it's positive. It's an endothermic process. Okay, so how do we determine if this thing is spontaneous? What do we got to do?
Delta G equation.
Delta G. Okay, so I'm gonna have to call on some people. Nick, can you calculate the Gibbs free energy of product A?
I'll give it a shot.
Thank you. And Alan, can you calculate the Gibbs free energy of product B?
Yeah.
Perfect, thank you. We'll give you a minute to do that. So you have the entropy and the enthalpy. You can solve for Gibbs. In case we don't remember, delta G is equal to delta H minus T delta S. Alan and Nick, you remember that?
Yeah, I remember.
Yep, I had that.
All right, and let's use 298K.
I got a really big number. I think I might have did something wrong.
I did too. I got a really big negative number.
Can you turn it
take a shot at mine?
into? Can you turn it into kilojoules per mole instead?
Oh, that's okay.
And did you keep your units consistent? Remember,
Nope, I forgot about that.
and entropies in joules and enthalpies in kilojoules.
Forgot about that too.
Yes. I thought that might happen.
So what are the units for the answer? Kilojoules or joules?
Kilojoules per mole, yep.
Okay.
Okay, for product A, I got negative 3.704.
Okay, and that's kilojoules per mole.
Yes. Okay.
Perfect. All right, everybody get that? So he used the Gibbs equation. He came up with negative 3.7 kilojoules per mole using the Gibbs equation. One thing people always forget is to keep those units consistent, right, between the entropy and the enthalpy, but we got it figured out. Okay. Alan, what did you come up with for product B?
I'm kind of confused because you said kilojoules, right? Am I supposed to use the enthalpy we calculated from the last question? So
Mm-hmm.
oh, so it was 5, right? So it was
Yep.
5 divided by 1,000. So it'd be 0.005. So then if I plug that in, 298 times.
So why are you dividing by
I thought because
1,000?
I thought we calculated the enthalpy of B, which was 5, and that was that in kilojoules, right? Oh wait, that's already in kilojoules. Never mind.
Yeah.
So
Yeah, it's in
I do
kilojoules.
5
So
minus
better convert the
298.
entropy.
I'm sorry. Could you repeat that?
Better to convert the entropy into kilojoules.
Ah, okay, gotcha.
So here, let me share my screen. So we'll take, so the delta G is going to equal 5 kilojoules per mole minus 298 times positive 53.8 that we're going to convert to kilojoules. So 0.0538. And that's in kilojoules per Kelvin mole. So we're consistent with the kilojoules here.
So that would be negative 11.03.
Yep, exactly. So
All right.
everybody, Alan got 11 kilojoules per mole. Negative 11 kilojoules per mole. Okay, perfect. Okay, so we have done a thorough thermodynamic analysis. Oh, 1 second. I was trying to respond to you, Michael. No problem. Okay, we've done a thorough thermodynamic analysis. Okay, and what we found is that both of these products are spontaneous, right? One is negative 3.7 kilojoules per mole, and one is negative 11 kilojoules per mole. And so we can say here that maybe the product B, yeah, product B is more stable, more likely to form. Yeah, Jake, you're right. Negative 3.7 is right. Okay, so question number 5 asks us, well, which one is more stable or more likely to form, and that would be product B, okay, because it's more negative than product A. Okay, you guys with me so far? Okay, we got awesome. All right, we're gonna keep going then. We have number 6. All right, so we answered yes in 6. So the question here is, okay, so it might not always be spontaneous. When is it non-spontaneous? Okay, so we know that at 298 it's spontaneous. Oh, do you guys remember how to do this? How do we solve for that transition between spontaneous and non-spontaneous?
What you said, delta G equal to 0 and then solve for temperature.
Exactly, exactly. So we're going to do that. We're going to set delta G equal to 0, and we're going to use product B for this. And then we're going to solve for temperature. So essentially we're just taking the enthalpy divided by the entropy, and that gives you the temperature of that transition. All right, so Paulina, would you like to calculate this for us?
I could try.
Okay, so T is equal to the enthalpy divided by the entropy. And you'll get temperature out. All right, and again, we got to keep things consistent. So we could say 5,000 joules per mole divided by 53.8. All right, is that, you recognize that, Paulina?
Yes.
Okay. All right, so what do we get?
$204.
5,000 divided by 53.8. 93, there we go. Jake, what happened?
Well, don't you have to keep your units consistent? Because if delta H is in kilojoules, I converted my joules to kilojoules. Actually, what did I
You
do?
still get the same answer.
I'm trying to think what I did. So I took the 53.8 and I divided by 1,000. So I think that's what I did wrong.
Okay. All right, so it should be 93. So once we set delta G to 0, that's a transition between spontaneous and non-spontaneous. So we can say here that this reaction is non-spontaneous at temperatures below 93 Kelvin. Okay, so that's what we can say about this reaction. So it's not always spontaneous. Temperatures below 93 will be non-spontaneous. All right, we good so far? Okay. All right, so let us go on to the next problem at hand. All right, so now we're going to investigate different types of bases on this reaction. Okay, so what we see here, if we go to the next part, what we see here is that when we use LDA as our base, we get 99% of product A. Okay, so let's kind of forget about the thermodynamics for just a minute, and let's focus on the kinetics of this reaction. Okay, so we have 3 reactions, and we need to find out what the rate law of this reaction is. Okay, so we're given the concentrations of LDA and the concentrations of 2-methylcyclohexanone. We have a rate associated with each of those. Okay, so let's talk through this a little bit. When we search for a rate law, we always have to find an experiment where one thing changes and the other doesn't. Okay, so if I said, well, let's compare trials 1 and 2, what specific reactant am I looking at? Am I looking at the 2-cyclohexanone, or am I looking at the LDA? If I'm looking at 1 and 2. Yeah, LDA, thanks everybody. Okay, so we're looking at the LDA. So we're gonna focus on the LDA here and determine what is the order with respect to LDA. Okay, so if we look at trials 1 and 2, we can see that the concentration of LDA is doubled. What happens to the rate?
Stays the same.
Stays the same. So what can we say about the order with respect to LDA?
It's 0.
0 order in LDA. All right. And now let's compare trials 1 and 3, because here I am doubling 2-methylcyclohexanone and LDA remains the same. What happens to the rate between trials 1 and 3?
Doubles.
It doubles. Okay. So what is the rate with respect to 2-methylcyclohexanone? First order, second order, 0 order?
First.
First order. All right. So then we can write down the rate law. So we've looked at LDA, it's 0 order. We've looked at 2-cyclohexanone and it's first order. So the overall rate for the reaction, and this is how you would write that rate law, is rate is equal to K, your rate constant, times 2-methylcyclohexanol. I'll call it MCH instead of writing it all out. This is the rate law. This is the overall rate law based on that experiment. Okay, everybody still with me, right? All right, awesome.
You
Okay,
drop LDA because
so
it's 0, right?
yep, it's 0. So it's not part of the rate law.
Okay.
Okay, so let's calculate the rate constant based on our rate law. So when you calculate the rate constant based on a rate law, you use the rate law and you just put in the values from any of those experiments that you want. Okay, so I am going to ask Jaylene to calculate the rate constant for me. That sound okay, Jaylene?
I'll try.
What?
I'll try.
Sound okay?
Yeah.
Okay, awesome. So she's going to calculate the rate constant for us. One thing I'll add, Jaylene, is notice that the rate constant here is, or sorry, that the units here are in moles. You need to divide by the volume 0.05 liters to get the molarity. All right, Jaylene, what did you come up with?
Okay, I'm kind of having trouble like doing it.
Mm-hmm. Here, let me share my screen. All right, so what I'm going to do, so remember, I should not have cleared that. Rate is equal to K times MCH. Okay, so you can just put any old value in, and if you look at 1, it looks like we have 0.0355252. That's equal to K times the concentration here, which is 0.00234 divided by 0.05. All right, that'll give you a concentration. All right, is that helpful?
Yes.
Okay, so let's solve for K. All right, what did you get, Jaylene?
I got 0.289.
Okay, good. Do you know the units?
K.
The units of K, yeah. All right, so the rate is molar per second, and that's equal K times molar. So what's the rate constant for, or sorry, what's the units for K?
Second.
Per second, right? So first order rate constant always has units of per second. All right, sound good, everybody? All right. All right, so the next part, what I'm gonna do is I'm gonna take you through what I did. And the reason I'm doing that is because, oh, Lisbeth, how can you explain to find units for other orders? Oh, that's an excellent question. I'm just gonna sidebar right here. and answer that question. Okay, so let's do a couple examples. So zero order. So I'm going to write some rate laws for, I'll go up to 3, okay? All right, so rate is equal to K, that's zero order. Rate is equal to K times, I'm just going to use an arbitrary letter A. So this is 0, this is first. Rate is equal to K times A squared, right? That's second. Rate is equal to K times A cubed, right? That's third, okay. So how do you find the rate? How do you find the units of K in each of these cases? So rate is always molar per second, okay? And so in concentration is always molar, okay? So to find the rate constant of K for a zero order, because rate is equal to K, the units for K are molar per second, okay? For first order, you have molar per second and you have molar over here. Divide by molar and you get per second. For second order, you have molar per second, and here you have molar squared. Divide by molar squared, and you have per molar per second. Okay. So here we have molar per second, and here we have molar cubed. Divide by molar cubed, you get molar per molar squared per second. All right, Elizabeth and Alan, was that helpful? Okay, this is definitely, that was a great question because this is definitely something you're going to have to be able to do, especially with these checkpoints coming up. You're going to have to know what those units are. And if you don't know it off the top of your head, you can figure it out doing this way. Right, sound good, everybody?
Definitely.
Okay, all right, so let's go on to the next part. And so the next part, I'm really just going to show you my work because we haven't really gotten to this part in lecture yet. This is exactly what we're going to do straight away next week. And that is looking at the integrated rate laws. And when you use the integrated rate laws, you are looking at time and concentration and how concentration reacts over time. So how the disappearance of your reactant over time, and that tells you the order of the reaction. And we're going to be looking at zero order, first order, and second order. So we're just going to do those 3 when we talk about the integrated rate laws. So I'm going to share my screen and show you what I did to work this problem out. All right, so this is the problem at hand. We have our reaction with 2-methylcyclohexanone. And in the last example, we used a base called LDA. And LDA is a really strong base. And what we're going to do is we're going to do the same reaction with another base, this triethylamine. And this is not a very strong base. And we're going to see if we still have the rate law that we saw before. Because remember, the rate law we saw in the other reaction was rate is equal to K times the reactant 2-methylcyclohexanone. So we're going to see now, is it still the same if we use another base? Because it might not be. Okay, so we have this data that we took over time. And we can see the concentration of 2-methylcyclohexanone decrease over time. And we can see the concentration of TEA over time also. So what we need to do is we need to look at the rate law associated with each reactant. All right, so what we're going to do is we're going to plot each reactant. So when you plot the reactant and you want to determine if it's first order, second order, or zero order, what you would do is you would, so for zero, you would plot the concentration versus time. So for first, you would plot the natural log of the concentration versus time. Okay. For second, you would plot 1 over the concentration versus time. Okay. And you would do that and you would determine which one of these is linear. So if I plot the concentration or the natural log of the concentration, notice that's what I'm doing here. Oops. Notice that's what I'm doing here. Plotting the natural log of the concentration versus time, you can see that I have a line. What that indicates is that I have a first order respect to 2-methylcyclohexanone. Okay, so that looks a lot like what we saw before at the LDA. All right, so then let's look at the triethylamine. All right, we look at the triethylamine and we can see if we plot the concentration of the triethylamine versus time, we have a line. All right, who can tell me what the order with respect to TEA is? We're plotting the concentration versus time. What does that mean? Just go ahead and shout it out. I know you're thinking it.
Zero order.
Zero order, right? So if we're plotting the concentration versus time and it's linear, it's zero order. Okay, so we have the same rate law that we saw before with the LDA. So we can say that the rate is equal to K times the concentration of that 2-methylcyclohexanone. Okay, so that's how you would do it graphically, and we're going to do a lot of this next week. All right, I believe that's the end of the worksheet. Am I right? Oh, let's move on. Let's move on to number. Is number 11 on your worksheet? Let's just quickly look at that because this is really interesting. We're comparing the rate constant of LDA and TEA. All right, so let's remind ourselves, what was the rate constant for the LDA reaction?
Per second.
That's the units.
Oh, whoops.
Jaylene did it. Do you remember what you got, Jaylene?
Oh, 0.29.
There we go, 0.29 per second for the LDA. All right, and if we look at those graphs that I just showed you, so I'm gonna, here, I'll share my screen again. All right, let's look at those graphs I just showed you. What shows you the rate constant is this value, the slope, okay? So here the slope is 0.2556 per second. We'll say 0.26. All right, so those are the rate constant. And the question is, which reaction proceeds faster?
Would it be TEA because that has a smaller number?
Oh, it's actually exactly opposite of that. The bigger number because it's faster.
So I might have been the opposite because if it's a per second, it would be an inverse second. So if you're trying to get wholer towards 1 or towards 0, wouldn't you be closer towards a positive value and be larger? But all right, I got you.
So per second really is a frequency, right?
Yeah, I think it hurts when I hear that.
Yeah, that's exactly what this is. So how many molecules turn over per second?
Oh, okay. Yeah, all right.
Yeah, lots of times people use rate constants as a turnover number too. You can turn, right?
All right.
So this many molecules per second,
All
essentially.
right, that makes more sense now.
All right, so we decided that the LDA is going to go faster. It's a better base. It makes sense that it's going to go faster than the TEA. All right, so that's all we have for today. Do you guys have any questions, anything that you want to go over? I liked that question about the units. That's very timely. All right, so we're good.
Yep, I'm good.
All right. Thank you everybody for coming. I will send this on to your instructor so they know you were here and you get credit for it. You guys were awesome. I liked that you worked together with me. It was a great time. All right, bye-bye everybody. Take care. Have a good evening.
Thank you.